Okay. Make sure this all works. Let's see. Let's see a slideshow. Yeah. Well, hello, everybody. Thank you for this opportunity to speak to you at this meeting. I'm trying to lecture today on evaluating water through evaporation, using experiences from California, which is a semi-arid landscape, very much like the semi-arid and arid landscapes that you're working with here in the Middle East. I have had a long interest in studying evaporation. I grew up on a walnut ranch in California, and this is a picture of me trying to irrigate our walnut orchard. So I have a lot of firsthand experience trying to manage water in a arid, semi-arid environment here, essentially. My big picture goal, one I hope that's relevant to all of you in the audience, is to really understanding how to quantify and assess evaporation everywhere all the time. And for my own work, California is an ideal model that is relevant worldwide because we have a wide range of ecosystems and microclimates. A Great Central Valley is essentially a desert with 300 millimeters of rain per year, and it's fed by irrigated agriculture from water runoff from the Sierra Nevadas. If you go to the south, we have expanses of desert, essentially, that are very much like the Middle East. We have the Pacific Northwest that is very green and verdant, that might get over 2,000 millimeters of rainfall, essentially. And then we have our mountain ranges here. And so I think a lot of lessons that we're gleaning from studying evaporation in California is I think, applicable to the rest of the world, essentially. Over the years, I've kind of taken a biometeorological, ecophysiological, ecosystem science view of this. My training was in atmospheric science and agricultural meteorology, and so I take courses from people like Bill Pruitt of FAO ET fame. But also over the years, I've had a lot of experience working with natural ecosystems. And so this cartoon, I think, helps give a framework for the data and the information I'll show you. Clearly, when we want to think about evaporation, we have to think about available energy. So that's the amount of sunlight that is hitting the system, the amount of long wave radiation that's coming from the sky, but what's available. So we have to subtract the reflected short wave and the emitted long wave. And that available energy is very much a function of how much green vegetation there is, the leaf area index. Once we absorb that energy, some of that can be used for latent heat exchange and transpiration. But other aspects will affect how much that occurs. Partly gets back to the stomata, the pores on the leaves, how open, how closed they are. That in firsthand is going to be affected by soil moisture. So clearly the losses of soil moisture through evaporation versus the inputs from rainfall will have an impact on how open and closed the stomata are. As we work to other ecosystems that might have more rainfall and surplus rainfall, we also have to bring in the carbon cycle and the nutrient cycle. Because ultimately the stomata open to optimize carbon uptake to minimize water loss, and this is done at the cost of nutrients, nitrogen, essentially. So it's this cartoon that I use to help me think about how evaporation will vary from different parts of the world, and arid and semi-arid. And this is the framework in this cartoon that was applied to produce this map here, essentially using mechanistic models that couple carbon and water and being driven with high resolution remote sensing, that 1 meter resolution. So to understand and achieve that map, that painting, we have to do a lot of basic research. So we've been working on this for 40 years to get to this stage. And some of the first basis is just getting some data. And so we want to know what the seasonal, the annual evaporation is of managed and natural ecosystems. And we can do this with what's called the Eddy covariance method. Once we have that information, we want to know how it's changing on seasonal and annual values. And this is where we have to think about things like phenology, length of growing season. When do the plants green up? When do they senesce? Are they evergreen? Are they perennial? Are they annual? Management plays a big role in terms of harvesting and planting and timing. And then clearly the amount of leaf area affects available energy. And again, if you're in semi-arid, arid conditions, that reduction in soil moisture will cause the closure of stomata. And clearly we're living in a new world, a warming world, one with elevated carbon dioxide levels and booms and busts in rainfall. So what do we expect the evaporation budget to be into the future? For those who may not be familiar, our measurements are a direct measurement, and we use what's called the Eddy covariance method. Essentially, we put a set of sensors on a tower that measure the evaporation from a huge footprint of plants, trees, soils, upwind. We measure instantaneous vertical velocity fluctuations, and with each updraft and downdraft of air, we actually measure the changes in temperature, humidity, carbon dioxide. We do this 10 to 20 times a second. We average this over half hour to an hour, and we produce this so-called flux of water. What's nice is it is one of the most direct methods. It is in situ without affecting the thing you're studying. And we essentially have records up to 20 years now, essentially, of these measurements. Once we have these measurements, we still want to interpret them and quantify them. I want to give you a sense that it's more than just cartoons that I give you. We try to use a theory. The Penman-Monteith equation is the one I like to use. It really is a nice balance between the supply and demand that helps us understand the late heat evaporation. I don't know if you can see my arrow here, but the terms are the available energy here. There's an evaporative demand by the humidity deficit and the mixing of the air, how windy it is. But it's also divided by a term called the surface conductance. And it's that surface conductance that's very important that we're trying to quantify. It's a function of leaf area index, the molecule conductance, leaf nitrogen, soil moisture. As I move on, I'll give you some examples of our work, some contrasting cases, which I think are relevant to this community here. We'll look at some rice, which is irrigated clearly. Same with alfalfa and corn, because there's lots of irrigated agriculture I see in Saudi Arabia. And then we'll look at some lessons from native ecosystems, our annual grasslands and savanna. One thing about using the Penman-Monteith equation to understand evaporation, it gets back to certain conditions when certain processes are more controlling than the others. What I plotted here is actually latent heat exchange or evaporation divided by the equilibrium rate, which is essentially a term normalized by the available energy. What you may have heard in the past is when we have what's called potential evaporation, this ratio between LE and LEQ is about 1.26. This is the so-called Priestley-Taylor rate. What's interesting about this curve here is that we can maintain potential evaporation at the Priestley-Taylor rate for surface resistance up to about 100 seconds per meter. Well, what does this mean? Well, most often, if you're dealing with agricultural vegetated conditions, closed canopy, leaf area index of 3 or 4, the crops are irrigated, crops are fertilized, so there's no stress in the stomata, and there's ample open stomata for photosynthesis. We kind of maintain this condition of potential evaporation, where evaporation rates will vary now and actually decline from the potential are with these other ecophysiological effects. Corn, for example, can be looking like a wheat canopy. It's tall, it's irrigated, it's very green, but it's a C4 plant. And a C4 plant has doesn't have to open its stomata as open. So you can actually see a water savings between the wheat and the corn. Temperate forest has even lower rates of normalized evaporation. Again, it's a very green vegetation, ample moisture, leaf area indices of 5, but it relies on its natural nitrogen cycle. And so the plant's leaves are not as productive. Their photosynthetic capacity is not so high, so they use less water. And then clearly, as we go to a boreal forest and oak savanna, we have even less rates of evaporation from these natural systems. They have higher surface resistances. The oak savanna, because the stomata closed over the course of the season due to the drought, And the boreal forest, because it's so cold, it's got a short growing season. It's the decomposition cycles are slow, essentially. So that, in a way, we can kind of map out this on this figure here. But there's some exceptions. So let's start with the rice. I think this might be very relevant to the audience here. You can see the rice is very green. It's ample water, irrigated. But we see lots of interannual variability in our annual sums. First of all, we reach about a meter of water. So rice in a semi-arid place has a high expense. The interesting thing is crop productivity scales with evaporation. So we can have high productivity, but at the expense of high water. But we also see year-to-year variation between maybe 800 and 1200 or 1100 millimeters of water. So, why is that occurring? Well, one thing is phenology. We had a couple of years where we had wet rains in the winter, and so the growing season was delayed. It took a while for them to plant, and so they didn't plant until maybe May or so. Other years we had droughts, and they were able to plant sooner. So length of growing season, one factor. But the other issue is we had conditions in the early years where we far exceeded potential evaporation. Instead of reaching the Priestley-Taylor rate of about 1.26, we had a ratio of about 1.5, 1.4. And then with time, we approached 1.2 or so. Well, what happened? Well, we have infection. And so you all know well the oasis effect. And we see this very much with our rice. The first year, we had a small rice field here, surrounded by dry fields, corn, other things. And so the heat from these other fields advected and enhanced the evaporation from the rice. The subsequent years, we had bigger rice fields, and then we planted some wetlands nearby. And so as the region started to get humidified, that oasis effect declined. So I guess the lesson for here is that the amount of evaporation you may see in an semi-arid irrigated condition will depend on how isolated that system is or how entrained it is into a larger mosaic of irrigated fields. Alfalfa is the other one we are growing. And again, places like California have actually become the so-called dairy state. Wisconsin used to be the dairy state where they used to have a lot of cows and milk and forage plants. But again, it's a cold place, short growing seasons, and they don't get many cuttings of alfalfa. So in California with irrigation, we can get 5, 6 cuttings of alfalfa. And so you can see between cuttings, you might reach up to 5, 6 millimeters of evaporation per day. You do the cutting, you reduce leaf area index, you get a drop, but then as it grows again, evaporation increases. We also see advection at this site. And just for reference, when I was a grad student in Nebraska, my professor Norm Rosenberg actually observed evaporation rates up to 14 millimeters of evaporation per day in alfalfa. So it's a very heavy water feeder. So again, when you're thinking about crops you may or may not choose, you have to make these choices about your water. Corn is also grown nearby, and ultimately, based on what I've mentioned a few moments ago, you can have these 2 fields within 500 meters of each other, and one's using about 750 millimeters of water a year. The other one's using between 850 and 950 millimeters of water. Just because one's a perennial, has long growing season, it's a C3 crop. The other one's an annual, a C4 crop. So again, you start seeing the knobs that we're turning by changing the types of vegetation, the types of management. And lastly, the lesson I want to kind of go back to native ecosystems. So now we're relying on nature's water. In California, we see huge interannual variability of rainfall, up to 30% per year, essentially. So we do have these booms and busts, essentially. We rarely have more than 2 years of drought, which is good. So we have some dry periods and increases. The interesting thing now, over this 20-year record or so, we have not really seen a significant trend in evaporation. Some of the back of the envelope calculations are thinking that in many parts of the world, we would get higher water use, which is a big problem in semi-arid conditions, because the idea is that the saturation vapor pressure of a wet surface, like a transpiring leaf, will increase. It will cause a stronger gradient of moisture, humidity between the leaf and the surface that would enhance that. But going back to Monteith's work, there's this idea of this balance between supply and demand. Warming also leads to more long wave energy loss, also more sensible heat loss. So there's less valuable energy to drive evaporation increase in a warmer world. So both theory and observations are actually showing things fairly flat. Now, does this happen elsewhere in the tropics and temperate forests? We don't know. But we do see this in our semi-arid conditions in California. One of the unique things about this ecosystem is that it does tap deep groundwater, stuff that we often don't see. We had to drill wells. And so the depth of the groundwater based on the snowpack in the Sierra Nevada helped higher evaporation on the wetter years and led to lower on the lower years. So we also have to think about stuff we don't see, the groundwater. And ultimately, I think this is a nice distillation of kind of the rules we've learned that I think will be applicable to this audience. When we want to think about how much water is going to be used by dryland ecosystems, we really have to think of this laws, these ecological and physical laws. For the plants to be sustained, obviously photosynthesis has to exceed respiration, okay? That comes at a cost. We need to use water. The stomata are open, there's transpiration. With our seasonal rainfalls in California, we have lots of water in the wintertime when the plants and trees are deciduous, but once the leaves come out, they have a very short growing season of available water. So to meet this condition, they have to do a couple things. One is they have to have stomatal closure so they can maintain evaporation rates that are less than the rainfall. Okay, that's part one. That's a physiological one. The second one is they have to set up a savanna system. They cannot afford to have a closed canopy. So by reducing leaf area index and forming a sparse canopy, you also increase that surface resistance. And so you reduce water use by the whole landscape, essentially. But now they have to do something to make sure their photosynthesis exceeds respiration. And that gets back to the nitrogen cycle. They have to produce leaves that have very high photosynthetic capacity for the short period so they can have high enough rates of photosynthesis. And that comes with having enough nitrogen to do so. So I think this has been helping us think about how these systems work in these dry systems here. So I'd like to conclude. I think we all are going to agree that water is a very precious commodity in the semi-arid and arid regions of the world. I think we need to manage it fairly and realize it has to be shared among multiple legitimate stakeholders. In California, this is a big issue. Agriculture, cities, rivers, fish all want water, essentially. Our famous author, Mark Twain, says, "Whiskey's for drinking, water's for fighting over." And we really have to think more scientifically of how we're using water to use it more fairly, essentially. I hope with this talk, I've given you some tools that we can think of the knobs that we can turn to maybe think about optimizing water use better among our stakeholders. And ultimately, we want to maybe think like a tree when we monitor water in dry ecosystems. So again, I thank you for this opportunity to speak with you. I wish you the best on your workshop, and I hope you found this useful. I will stop.